Continuing on physical chemistry, chapter 4, now we're starting section 6. We're going to be calculating the changes of state functions. Now remember a while ago we talked about we wanted to find the entropy change for a general change of state for an ideal gas, P1, T1 to P2, T2, said we're going to have to skip it. But now that we've done the Maxwell relations and so on, we can do this. And remember, entropy is a function of temperature and pressure, so we can write the differential of entropy as the derivative of entropy with respect to temperature holding pressure constant times the differential of temperature, plus the derivative of entropy with respect to pressure holding temperature constant times the differential of pressure. Now, we're going to use the Maxwell relations and the definition of alpha to substitute this out. So we're going to get ds is equal to Cp over T with just dt minus alpha V dP. Now we're going to integrate that. So we'll get delta S is equal to the entropy at state 2 minus the entropy at state 1. And that's going to be the integral from state 1 to state 2 of Cp over T dt. And that's going to be minus the integral from state 1 to state 2 of alpha V dP. Now these are line integrals, and we're going to just look at them separately because they're with respect to different variables and so on. So we're going to say that A is equal to the definite integral from state 1 to state 2 of Cp over T dt, and that B is equal to the integral from state 1 to state 2 of alpha V dP. So the change in entropy for part A is going to be the definite integral from temperature 1 to temperature 2 of Cp over T dt. And we're going to assume that's a constant pressure, of course. Physical chemistry, chapter 4, section 6. We're talking about calculations of changes in state function. So we're continuing on how do you find delta S if we're going from state P1, T1 to P2, V2. And we divide it into two steps, A and B. Then for the second step, B, the change in entropy is going to be the definite integral from pressure 1 to pressure 2 of alpha V with respect to pressure. And that's while T is constant. So graphically, you can see what we've really done is we're going from P1 to P2 in any manner. It doesn't really matter. But entropy is a state function, so we just find any path to get there. And the path we've chosen is to do a constant pressure process and then a constant temperature process, because we know how to do those. And of course, entropy is a state function, so the total change in entropy is just the change in entropy for step A plus the change in entropy for step B. Okay, coming up next is physical chemistry, chapter 4, section 6. We're talking more about calculations of changes in entropy functions. Now we're going to talk about a phase transition. What if we have a phase transition that's irreversible? Like let's say we go from H2O solid at minus 5 degrees Celsius 1 atm. And somehow we just irreversibly go from all the way to liquid water at positive 5 degrees Celsius at 1 atm, holding pressure constant. Well, since it's irreversible, we can't really do that directly. But S is a state function, so if we find a reversible path to do the same thing, we can end up with the same calculations. So what we've done is divide it in 3 steps. One, we're going to heat it up to the melting point, then we're going to melt it, and then we're going to heat it up some more to this other temperature. So we have delta S1 for a reversible step to the melting point, delta S2 for the change in the entropy of melting, and then the delta S3 for some more reversible heating up to our final temperature, minus 5 or positive 5 degrees Celsius. So delta S1, we just integrate from the minus 5 degrees to 0 degrees of the heat capacity for solid water or ice divided by temperature with respect to temperature. Then for step 2, the change in entropy is just going to be the change in enthalpy of transition, melting in this case, divided by temperature. And then for the final step, heat it up some more, that'll be just the change in entropy for step 3 is going to be integral from 0 degrees Celsius to 5 degrees Celsius of the heat capacity of liquid water divided by the temperature with respect to temperature. And since S is a state function, then we know the total S from here to here, no matter which way we go, is just going to be delta S1 plus delta S2 plus delta S3. Coming up next, physical chemistry, chapter 4, section 6. We're calculating changes of state functions. Now we're going to calculate delta H and delta U if we're going from state of pressure 1, temperature 1 to state pressure 2, temperature 2. Now we know that enthalpy is a function of temperature and pressure. So writing out the differential of H, we get the differential of H with respect to temperature, constant P dt, and the differential of H with respect to pressure holding temperature constant dP. And we know that Cp is the derivative of enthalpy with respect to temperature holding pressure constant. So we can substitute that back in, and we're going to get then delta H is equal to the integral from state 1 to state 2 of Cp dt plus the definite integral from state 1 to state 2 of V minus T alpha V dP. Now that's assuming there's no phase transition. So if we have no phase transition, it'll be just delta H equals delta H of step A plus step B, or however you want to look at that. If there is a phase transition, of course you can just throw that in there because it's a state variable. So delta H is just, delta H of step A, delta H of step B, delta H of that phase transition. Now we know that U is a function of T and V, but volume can change with pressure, so you could write internal energy as a function of temperature and pressure instead. That'll give us du is equal to the derivative of U with respect to T holding volume constant times the differential of temperature, plus the derivative of U with respect to V holding temperature constant times the differential of V. And then if you just integrate that, you'll get the delta U you're looking for. Physical Chemistry, Chapter 4, Section 6, we're continuing with calculations of changes in state functions. Now we're going to calculate the change in the Gibbs free energy and the Helmholtz free energy. Now for an isothermal change, we'll do that first. Delta G is equal to delta H minus T delta S, and we can only evaluate this at constant temperature. So the differential, we also know dG is equal to VdP minus SdT. And if we're going to hold it at constant temperature, this term SdT is equal to 0. So then we just get dG is equal to VdP. Now we showed before, when we did the Gibbs equations, the Maxwell relations, that the derivative of G with respect to P at constant T is equal to V. So the change in the Gibbs free energy is going to be the integral from pressure 1 to pressure 2 of V as a function of pressure dP. So we can evaluate that as long as we have a formula, an equation of state, for volume as a function of pressure. Now we do for an ideal gas. It's called PV equals nRT. So you just solve for V and you substitute in. So for ideal gas, perfect gas, you get delta G is equal to the definite integral from pressure 1 to pressure 2 of nRT over pressure with respect to pressure. Now another case we're going to look at then for delta G is at equilibrium. Now we know that delta S is equal to Q reversible over T, so T delta S is equal to Q reversible. And we also know that at constant pressure, delta H is equal to Q. So then what we have is delta G is equal to delta H minus T delta S, so that would just give us Q minus Q, and that's equal to 0. So we know that at equilibrium, delta G is equal to 0. Now this is a graph of our Gibbs absolute versus our reaction coordinates here. So this is going to show, we know that G gets minimized at equilibrium. We haven't really shown that yet, but we will. So obviously where it's minimized, the derivative or differential is going to be equal to 0. That's what we just showed. Continuing Physical Chemistry, Chapter 4. We're on Section 6 now. We're just finishing up Section 6 actually. We're doing calculations of changes in state functions, namely delta G and delta A. Actually, we just finished delta G, now we'll do delta A. So we know there's two different ways to find delta A actually. So one, we start with dA is equal to minus SdT minus PdV, and we're assuming constant temperature. Oh, well, if we're at constant temperature, I mean, dA then would be just minus PdV because the other term drops out, equals to 0. So delta A would just be the integral from volume 1 to volume 2 of minus PdV. Another way to look at it, though, would be start with delta A is equal to delta U minus T delta S. We know that delta U is equal to Q plus W, so delta A is equal to Q plus W minus T delta S. We also know that Q is equal to T delta S, so delta A is equal to T delta S plus W minus T delta S. These terms cancel out, So we're left with delta A is equal to W, which everybody knows is minus PdV. Okay, Physical Chemistry, Chapter 4, Section 9. Now let's do an example to find the extent of reaction. We're going to take nitrogen and hydrogen and make ammonia. So we're going to take 20 moles of nitrogen and 60 moles of hydrogen to get 40 moles of ammonia. Now we know that for the nitrogen, the change in the number of molecules is going to be minus 20, because we went from 20 molecules down to 0 molecules, or 20 moles down to 0 moles, so that's minus 20 moles. Now, our stoichiometric coefficient, nu, is minus 1 because it's a reactant. So we pull out the minus 1, and our extent is 20 moles. So nu is minus 1, extent is minus 20. The same for your hydrogen. We're going to lose 60 moles because we started with 60. We're going to end up 0 because it's the reactant. So again, our stoichiometric coefficient nu is going to be minus 3. So pull out the minus 3, and we get nu is minus 3, and the extent is 20. And then likewise for the ammonia is a product. So we're going to take 40 moles. We're going to factor out the plus 2 because it is a product. So we get nu is equal to positive 2, and the extent is 20 moles. So notice the extent for the reaction is the same everywhere. That's why it's called the extent of the reaction. And that's a useful quantity if you're going to be calculating some stuff later on. So another way to put that, find the extent, you just take the number of your substance final minus number of the same substance initial and divide by a stoichiometric coefficient. That's how we did that. Okay, let's do another example here. Let's say we're going to burn, what is this, propane with oxygen and get carbon dioxide and water. And so we're going to have nu for the propane is equal to minus 1. Nu for the O2 is equal to minus 5, because those are negative because those are reactants. Nu for the CO2 is positive 3, and nu for the water is positive 4 because of their products. Now let's say we use up 2 moles of oxygen in the reaction above. So we're going to say we start with positive 2 moles, end up with 0 moles for the calculation in this case. So delta N2 is just the NO2 final minus the NO2 initial, and that's equal to the extent times the nu of O2. Well, we know the extent is just NO2 final minus NO2 initial divided by nu O2. We're going to end up with 0 moles, so we're going to take away 2 moles because that was our initial moles, divide by 5. So the extent of this reaction is a fraction, 0.40 moles. So yes, extent can be a fraction, decimal, however you choose to write that. Continuing on Physical Chemistry, Chapter 4, Section 7, we're talking about open systems now. First we're going to talk about a system that has a single phase, but k components. K is any number, 1, 2, 3, any integer. So here's our system. It's a test tube, and it's an open system. It's open to the air, whatever, the surroundings. So we only have one single phase, like an aqueous solution or, I don't know, liquid metal alloy, something. And it's got k components, so it has whatever is in it. So before we had just G would be a function of T and P, but now we've got different components. So G is a function of temperature, pressure, the number of moles of component 1, the number of moles of component 2, the number of moles of component 3, all the way to the number of moles of component K. Because any component you add or subtract is going to change the total Gibbs free energy of the system. So before we just had dG is equal to the derivative of G with respect to T holding pressure constant dt, and the derivative of G with respect to pressure holding temperature constant dP. But now we have to do it a little more elaborate. What we have to do is talk about what about all these substances too. So if the derivative of G with respect to T holding pressure and all the number of molecules constant, just like before, dt, and derivative of Gibbs free energy with respect to pressure holding temperature and all the different molecules constant, dp. And then we're going to add up the change we have from all these different substances. So the derivative of G with respect to the first substance holding temperature and pressure and all other substances constant. The derivative of G with respect to the second substance holding temperature and pressure and all the other substances constant. The derivative of G with respect to the third substance holding Tp all the way up to K substances. So this is summation notation. So we're going all the way from the first substance to the kth substance. Yeah, right here. So what we're going to do is we're going to define the chemical potential as this quantity right here. So, and we're going to use mu, even though we already used mu for the Joule coefficient and the Joule-Thomson coefficient, but now we're going to use mu for something else. So mu is the derivative of the Gibbs free energy with respect to the number of molecules. And we're going to have a different one for each substance. So the chemical potential of substance 1, substance 2, substance 3, etc. So this, and it's going to be with the temperature and the pressure and all other substances held constant. So like I said, mu sub I is the chemical potential of substance I. I guess I could have left it that way, just mu is chemical potential. Now remember, G is an extensive quantity. N is extensive because it's just the quantity of molecules. But we're dividing extensive by extensive. So mu is an intensive quantity. Now chemical potential, this is important because this is the driving force behind chemical reactions. So far in this class we haven't really done much chemistry because we haven't really set up the mathematical foundation to handle it yet. But we're going to be doing chemistry soon enough. Now along the same lines though, you could use all your other types of energy. So you could have mu sub I as the derivative of internal energy with respect to the number of molecules holding entropy and volume and all other substances constant. Or the derivative of enthalpy with respect to your substance holding entropy and pressure and all other substances constant. Or the derivative of your Helmholtz free energy with respect to your substance holding volume and temperature and all other substances constant. Okay, physical chemistry, chapter 4.7, we're talking about open systems. We already started talking about what if we have a system with this one phase but k components in it, like in the diagram of a test tube over there. And we came up with chemical potential with this summation over here. Now originally we showed it like this. So dG is equal to minus SDT plus VdP plus the sum from substance I1 to I substance K of mu of substance I times the differential of substance I. But it could also be written du equals TdS minus PdV plus the sum of from 1 to k from mu I dni. Or dA equals minus SDT minus PdV plus the sum from 1 to k of mu I dni. Or dH is equal to TdS plus VdP equal to the sum from 1 to k of mu I dni. Continuing on physical chemistry, chapter 4, section 7, we're talking about open systems. Now we're going to talk about what if we have a system with more than one phase. Now, be careful because we're going to be reusing a symbol for another meaning. We're going to use alpha to be an index, to mean any phase in our system. Keep in mind we already defined alpha as something else, and that was 1 over v times the derivative of v with respect to temperature constant v. It's the exact same symbol, but by context you have to know it means this index, not that. So let's look at an example here. The differential of G is equal to the sum of the differential of G for each phase. So phase 1, phase 2, phase 3. Add up all the phases and you get the total differential of G. That's because G is a state function. So remember what we had before for dG is equal to SDT plus VdP. But now we're going to do it for each phase. So the dG is going to be minus SDT for phase 1, SDT for phase 2, SDT for phase 3, etc. Likewise, we're going to add up all the VdPs for all the different phases. So we're going to have VdP for phase 1, VdP for phase 2. So that's what the symbol means. The superscript alpha does not mean we're an exponent. We're not taking entropy to any power. It just means the entropy of alpha phase. And we're doing a double summation notation over here. So remember before when we have one phase, we just had the sum of all the substances I, substance 1, substance 2, substance 3, all the way to substance K, of mu I dni. But now we're going to do that for each phase. So for phase 1 we have this sum, phase 2 for this sum, phase 3, all the way to how many phases we have. So again, this superscript up here, alpha, means we're talking about phase alpha. It is not an exponent. But now we're going to rewrite the chemical potential and say, okay, the chemical potential for phase alpha is the derivative of Gibbs free energy in phase alpha with respect to the number of molecules changing for substance I in phase alpha. That's holding temperature, pressure, and all the other substances in phase alpha constant. Now, we know if we add up the entropy in phase alpha for the different phases, alpha, phase 1, phase 2, phase 3, we're going to end up with a total entropy because entropy is extensive. Likewise, the total volume. If we add up the volume in phase 1, volume in phase 2, volume in phase 3, add up all the phases, that's going to be the total volume of our system because volume is extensive. So what that tells us is even though we showed here SDT specifically for phases, we know for the total system then it's just like we had before. dg is equal to minus SDT plus BDP, but we still have this double summation notation. There's no way to simplify that. Continuing on physical chemistry, chapter 4, we're finishing up section 7 now. What about material equilibrium? Now we're going to say that T is constant and P is constant, so we know the differential of P is 0, the differential of temperature is 0, and we showed before then that the differential of Gibbs free energy is also going to be equal to 0. So simplifying that out, we're left with this sum must then also be equal to 0. So remember this sum, I means all the different substances I in each phase, and then alpha means all the different phases. So we're adding up the chemical potential with times the number of change in the number of molecules. You know, that has to be equal to 0. This is not very important. This is actually a condition for material equilibrium. It's assuming we're at constant temperature and pressure, though. Otherwise, those other terms from the Gibbs equation wouldn't be equal to 0. And this assumes PV work only, but it works with constant volume too. Now let's compare phase equilibrium versus reaction equilibrium. We know that for one phase, mu sub I was defined as the differential of Gibbs free energy with respect to the substance I, holding temperature, pressure, and all other substances constant. We know that G is a function of temperature, pressure, and all the different substances. Therefore, mu sub I must also be a function of temperature, pressure, and all these other different substances. And we also know that mu is a state function. Now, for more than one phase, or if we have only one phase, only one component, then mu sub I simplifies, and it's just the differential of G with respect to component I, but there is only one component. It's 1. And temperature, pressure, there are no other components. So, with only one phase and one component, mu sub I is just equal to the molar Gibbs free energy of that substance. But again, that's assuming only a pure substance. Coming up next, physical chemistry, chapter 4, section 8. We're going to derive the condition for phase equilibrium. Let's say we have some solid silver chloride in equilibrium with some aqueous silver chloride. So I drew it over here. We got our test tube. It's an open system, but that doesn't matter. So we're assuming our silver chloride is in two phases. At the bottom, it's in the solid phase. We're going to call that beta. And then above that, we're going to have an aqueous phase with some HgCl dissolved. We're just going to call that our delta phase for the purpose of notation for now. Okay, now we showed before that the double sum of our phase alpha and substance I of mu I dni is equal to 0. That's our condition for phase equilibrium. Now, if we put in the specific ones here, distribute that out, then we have the mu of substance J of phase beta, dn, the substance J, phase beta, plus mu sub J of phase delta, dn J, phase delta, and that's equal to 0. Now we also know we only have two phases, so whatever amount of silver chloride goes from one phase to the other, could also be written as minus the amount going from that phase into the other. It's just like we do with heat. Q out equals minus Q in or whatever. So we're going to take advantage of that. We're going to replace this dnj of beta with minus dnj of delta. So we get mu j in phase beta times dnj in phase delta plus mu j in phase delta, dnj phase delta is equal to 0. Now we're going to factor out that dnj in phase delta and get mu j phase delta minus mu j in phase beta. That's equal to 0. Now remember, when you have two things multiplied equal to 0, at least one of them has to be equal to 0. Now we're going to say that dnj phase delta, it can't be equal to 0, because basically you've frozen the system. You're not having anything going on. That's a really boring condition, so we're not going to look at that. Instead, we are saying, okay, molecules are going both ways, therefore, this other must be equal to 0. So what we can say then is that mu j in phase delta minus mu j in phase beta must be equal to 0. So you just solve and you get the chemical potential of substance J in phase delta is equal to the chemical potential of substance J in phase beta. That is our condition for phase equilibrium. That, of course, is assuming we have PV work only, that we're constant temperature and pressure, and, of course, our system is in thermal and mechanical equilibrium. Continuing on physical chemistry, chapter 4, section 9, we've been talking about the extent of the reaction xi, and we're going to simplify by just saying d xi is equal to 1. So it's basically going to disappear from our equations and go back to where we were before. So then we're going to end up with that the sum over substance I of mu sub I times nu sub I is going to be equal to 0, and that's when we're at chemical reaction equilibrium, assuming, of course, that we're in a closed system with PV work only. Now, furthermore, if we assume that we're constant temperature and pressure, then the differential of Gibbs free energy at constant temperature and pressure is equal to the sum over substance I of mu sub I dni. And that's also the same as the sum over substance I of mu I nu I times the differential the extent, like we had before that we set to 1. So then divided by the differential of xi, we get the derivative of Gibbs free energy with respect to xi is equal to the sum over substance I of mu I, or nu I, mu I. And that's equal to 0 when we're at equilibrium. For example, here's a graph of Gibbs free energy versus extent of the reaction, with pure reactants R at one end, pure products P at the other end. This isn't pressure, obviously, it's products. So at equilibrium, we know the derivative is equal to 0. So that's where it flattens out. If it's over here or if it's over here, it's not at equilibrium. If xi is greater than 0, that means the reaction has gone towards the products, like in the example we did before. If xi is less than 0, that means we started with too much products, so it's gone back towards the reactants. Continuing in physical chemistry, we're almost done with section 8 of chapter 4. Okay, let's talk about a system that is not at phase equilibrium. We showed before that if you're not at equilibrium, then dG is going to be less than 0, because our definition of equilibrium is minimizing the Gibbs free energy. So what that tells us is that the sum over phases alpha and substances I of mu I alpha dni alpha has got to be less than 0. Now, sort of factoring that out like we did on the previous slide with two phases then, the dn of substance J in phase delta is going to be, or times the mu sub I of delta minus mu sub I in beta is going to be less than 0. Now, we're going to say that dnj for delta is greater than 0. Why we're doing that is a bit complicated, but remember we said if there's any substance flowing, it's positive in one phase, negative in the other. So something's got to be positive somewhere. So we end up with mu j delta minus mu j beta is less than 0. Therefore, we can say that mu I, or mu j delta, is less than mu j beta. So we have, let's say we have two different substances here. One is they're both J. They're substance J in two different phases, beta and delta. But here, mu is higher than there. So it's going to spontaneously flow from up here to down there. So what we're saying is that we have a higher potential substance, it goes to a lower potential substance. Or actually, in this more realistically, we have substance and a higher potential in phase beta to the same substance, it'll have lower potential in phase delta. So what we're saying then is if mu j beta is greater than mu j of delta, then j will flow spontaneously from phase beta to phase delta. And in case you didn't pick that up then, mu sub j in phase delta being less than mu j of phase beta, or vice versa obviously, is going to be our condition for an irreversible process. Because obviously if your substance is going to spontaneously flow from one phase to the other, then it's not reversible, it's going to happen spontaneously. Continuing on physical chemistry, chapter 4, we're finishing up section 8. So we talked about equilibrium before, or actually different types of equilibria. So just to review, let's say that we have two phases, phase beta and delta. What does it mean that if those two phases are in thermal equilibrium? Then the temperature in phase beta is equal to the temperature in phase delta. What does it mean if those two phases are in mechanical equilibrium? Then the pressure in phase beta is equal to the pressure in phase delta. What does it mean if those two phases are in material equilibrium? That means the chemical potential of any substance J in phase beta is equal to the chemical potential of that same substance J in phase delta. Continuing on physical chemistry, we are beginning chapter 4, section 9 right now, reaction equilibrium. Let's say we have a generic reaction where substance A1, A stoichiometric coefficient, plus substance A2, B is the stoichiometric coefficient, etc. for all the reactants, goes to products A sub M with stoichiometric coefficient E, and substance A M plus 1 with stoichiometric coefficient F. Now, as an example, we'll put in benzene plus oxygen goes to carbon dioxide and water. So our A1 is the benzene, our lowercase a, the stoichiometric coefficient is 2, and then the other reactant, our A2 is O2, and its stoichiometric coefficient B is 15. They're going to products, so A sub 3 in this case would be carbon dioxide, and its stoichiometric coefficient E would be 12. And then the other reactant, or product, A4 would be H2O, and then its stoichiometric coefficient F is 6. Now, reactants and products, they can be any phase. We don't care solid, liquid, gas, whatever. It's going to work out mathematically the same. Now, we want to get all this on one side, so we're going to subtract the reactants from both sides. So we're going to go from 0 to minus A, A1, minus B, A2, etc. So we're going to have minuses for all the reactants, but we still have plus EAM, plus F, AM plus 1, etc. for all the products. Now we're going to use the symbol nu to mean this number here. It's the stoichiometric coefficient, but it'll be positive for all the products and minus for all the reactants. This is the same symbol you use for frequency, but obviously we're not talking about frequency in this case. So in this case, our nu sub 1 is going to be equal to minus A, our nu sub 2 will be equal to minus B, our nu sub M will be equal to E, and our nu sub M plus 1 is equal to F. So what we really have here, we're going to rewrite this in summation notation. So we're going to go from 0 to the sum over I of nu sub I times A sub I. It's an I, obviously. And like I already said, nu sub I is going to be less than 0 for all the reactants. Nu sub I will be greater than 0 for all the reactants. Now, then what we have here is that our total change in the number of molecules for each substance I is proportional to nu sub I. Remember, this is the same symbol alpha we use for other purposes, but in this case, it means proportional to. So what we need is a proportionality constant, and that's going to be this funny looking symbol here called xi. Xi is going to be our proportionality constant to convert this proportionality to an equal sign. Physical chemistry, chapter 4, we're continuing section 9. So the change in the number of molecules for substance I, we define as the current number of molecules for substance I minus the initial number of moles for substance I, actually. Now we define xi as the extent of the reaction, so it's this. We got the stoichiometric coefficient for I times the extent of the reaction. I'll do an example so you understand better exactly how that extent works. So remember, n sub I is the moles at any time. It can be right away or when you get to equilibrium or anywhere in between. Ni sub 0 is the initial number of moles that you had, if any. And then mu sub I, it has no dimension. That's basically the stoichiometric coefficient, except that it's positive for products and negative for reactants. And then xi is the extent of the reaction, and it's also in moles, which is actually a unit. So we have xi here is equal to Ni minus Ni sub 0 divided by nu I. So it's the current number of moles minus the initial number of moles divided by the stoichiometric coefficient. So this is how it works. Let's say we have some N2 plus 3H2 going to ammonia. And we're going to go all the way from just reactants to just products. So we're going to start with 20 moles of N2, start with 60 moles of H2. We're going to end up with none of that and just get 40 moles of ammonia. In that case, the change in the number of moles of N2 is just going to be minus 20 moles. So that's why nu I is minus 1, and the extent of the reaction is 20 moles. Likewise, for the number of moles of H2, we're going to use up all 60 moles. So nu I is minus 3, and the extent of the reaction is 20 moles. And likewise, we're going to create a bunch of product from 0 to 40. So the change in number of moles for NH3, ammonia, is 40 moles. So the nu sub I is plus 2 because it's a product. And the extent of the reaction is 20 moles. Notice, hopefully, that the extent of the reaction is the same for everything. That's why it's called the extent of the reaction. And it doesn't have the subscript I. These will change for the substance. This won't. Continuing on physical chemistry, chapter 4, section 9, more about xi and the extent of the reaction. Let's have another example. Let's say we have some, what would this be, propane? Okay, so we're going to burn some propane with oxygen, go to carbon dioxide and water. So for this reaction, nu of the propane is going to be minus 1 because it's a reactant. Nu of oxygen is going to be minus 5 because it's a reactant. Nu of carbon dioxide is going to be positive 3 because it's a product. And nu of H2O is going to be positive 4 because it's a product. Now let's say in the above, we have the above reaction and we're going to burn 2 moles of oxygen. Well, we're going to consume 2 moles of oxygen, I guess. What's the extent of the reaction? Well, we know that the change in the moles of oxygen is going to be equal to the current number of moles of oxygen minus the initial moles of oxygen. And that is equal to the extent of the reaction times nu for the oxygen. So solve for xi, the extent of the reaction, we get the initial moles of O2, or no, the current number of moles of O2 minus the initial number of moles of O2 divided by the nu of O2. So we get 0 moles because we used them all up. We're going to subtract out the 2 moles because that's what we started with. We're going to divide by 5 because that's what we said. Wait a minute, shouldn't that be negative? Yes, that should be negative 5. Alright, we're going to divide by negative 5 to get 0.40 moles for the extent of the reaction. Alright, some simplifications here. We're done with xi for now. Let's talk about a review of this chapter here. So remember we were talking about the equilibrium. Every substance I is going to be in phase alpha. So we have a double sum here. We have the sum over all the phases alpha and all the substances I of nu with respect to, times the change in the number of moles. And that's equal to 0. So if we rewrite that, we can, use parentheses however we want, because we're multiplying, we're doing a sum of this sum, basically. Is that how that is? Yeah. So we have the sum over I of mu sub I dni. Now remember, at phase equilibrium, our condition for phase equilibrium was that the mu for substance I in phase beta is equal to the chemical potential of substance I in phase delta. So remember, beta and delta are phases. Then we have the sum of I over I of mu sub I dni, that's equal to 0. That's our condition for material equilibrium. This says whatever substance I going out is the same as the substance coming back in. And then we have dni is equal to nu I times the differential of xi for chemical reaction, for the chemical reaction. Continuing on physical chemistry, chapter 4. This is the last of section 9 and the end of chapter 4. So to summarize, the chemical potential mu of substance I in phase beta is equal to the chemical potential mu of substance I in phase delta. That is our condition for phase equilibrium. And then 2, the sum of the nu for substance I times the chemical potential for substance I is equal to 0. And that's our condition for reaction equilibrium. Now we're going to show that I is actually a specific case for II. Well, those are Roman numerals. I guess you could say 1 is a specific case of 2. But anyway, so let's say we have a generic reaction where we're going from A of substance A in phase beta to A of substance A, or for substance in phase delta. And we're just going to set lowercase a is equal to 1, so it'll disappear. So then we have, again, our reactant, I, in phase beta, going to product, I, in phase delta. Well, I don't know if you should actually call it product or reactant. It's just a substance, I. Or rewriting that so it's on the same side, you get minus mu sub I in beta plus mu sub I in delta is equal to 0. Or yet another way, we can say that mu sub I in delta is equal to mu sub I in beta. So that shows that equation 2 is really just a more general form of equation 1. Now, what if substance I is not in phase delta at all? Well, then we have the inequality mu sub I in beta must be less than or equal to mu sub I delta. Because if it was the other way around, you don't have any substance to flow. And remember, it always goes from higher potential to lower potential. So if it's an equality, they're at the same height and it won't flow. Or if it's an inequality, then this has more potential. The vertical scale is potential, obviously. And then, so then it would flow spontaneously from phase beta to phase delta. For example, here's our test tube again. We have 2 phases. Arbitrarily set betas on the bottom, deltas on the top. And we have substance I in both of them. And this is the mathematical description of that system. So remember what we've said before already, that the chemical potential for substance I in phase beta is equal to the chemical potential of substance I in phase delta. That's our condition for equilibrium. But if it was an inequality, if the chemical potential in phase for substance I in phase beta is greater than the chemical potential of substance I in phase delta, then our substance I is going to spontaneously flow from phase beta to phase delta. Now, if delta has no I in it, like we said, then what this means is that there is still a value in phase delta for the chemical potential of substance I. And we find it the same way we did before. The chemical potential for substance I in phase delta is just the derivative of the Gibbs free energy with respect to the change in the number of molecules. And that's all for substance delta. And that's holding temperature and pressure constant, obviously.